Welcome back to the Dr. Liu VCE Physics channel. In this video, we'll go through the 2025 NHT Physics exam, focusing on questions related to gravitation and planet motion. My explanations may not be perfect, so if any teachers, parents, or students notice any errors, please feel free to offer your feedback. The magnitude of the acceleration due to gravity on Earth's surface is given as g. Planet Argus 3 has a mass that is 1.5 times the mass of Earth and a radius that is half Earth's radius. Since gravitational acceleration is proportional to mass and inversely proportional to the square of the radius, we can express the relationship as the gravitational acceleration on the surface of planet Argus 3 is 6g. Vesta, shown in Figure 4 below, is one of the largest asteroids in the asteroid belt, which is located between the planets Mars and Jupiter. A NASA probe named Dawn was sent to orbit Vesta in order to collect data on its geology and composition. According to Kepler's third law, for any two objects orbiting the same central body, in this case, the Sun, the ratio of the square of the orbital period to the cube of the semimajor axis, average orbital radius, is a constant. This can be expressed as: by comparing Earth's orbit to Vesta's orbit around the Sun, we can set up the following equality. By rearranging Kepler's third law to solve for the orbital motion of the Dawn probe around Vesta is maintained because the gravitational force exerted by Vesta acts as the necessary centripetal force. By equating the formula for the centripetal force with the formula for the universal gravitational force, and then algebraically rearranging the resulting equation, we can derive the orbital speed. This final equation allows us to calculate the required orbital speed based only on the universal gravitational constant, the mass of Vesta, and the orbital radius. When the Dawn probe is placed in a lower orbit, smaller radius, r, around Vesta, its orbital speed, v, must be increased. This is because the orbital speed for a stable circular orbit is inversely proportional to the square root of the orbital radius, as shown by the formula. Therefore, as r decreases, v must increase to maintain the balance between the gravitational pull and the required centripetal force. Two physics students, Chen and Darika, are viewing a live video stream from the International Space Station, ISS, which shows an astronaut floating around the cabin. Chen and Darika then have a discussion on how the force due to Earth's gravity is experienced by an astronaut floating in the ISS as they travel in a stable circular orbit around Earth. Chen states that the astronaut does not experience a force due to gravity in the ISS because there is no gravity where there is no air, and since space is a vacuum, no gravitational force can be experienced. Darika states that the force due to gravity is acting on the astronaut in the ISS, but her movement along with the spacecraft in a stable circular orbit around Earth creates a force that cancels out the gravitational force. Chen, incorrect. Gravity exists in a vacuum, no air. Darika, gravity exists, correct. Gravity always pulls the astronaut inward. Darika, motion cancels gravity, incorrect. The orbiting motion is a continuous fall caused by gravity acting as the centripetal force. There is no real outward force cancelling it. Circular motion does not create a force to oppose or cancel gravity. Gravity is the centripetal force that causes the astronaut to fall around the planet, resulting in orbit continuously. The opposing outward push is only a fictitious force, centrifugal force, experienced by the astronaut in the rotating. The only force on the astronaut and the ISS is gravity. Since both are constantly accelerating, falling, at the same rate, they are in continuous freefall, resulting in zero normal force and the sensation of weightlessness. This section accounts for 14 marks, 11.7% of the total score, and assesses understanding of fundamental concepts in gravitational physics and orbital mechanics. Multiple choice question 8, 1 mark gravitational field strength ratios. Calculating the ratio of gravitational acceleration, g, for a planet relative to Earth, based on mass and radius. Short answer question 5, 8 marks orbital mechanics calculations and analysis, Vesta's period, calculation of an orbiting body's period using Kepler's third law. Probe speed and orbital height, calculation of the probe's orbital speed and the analysis of how speed relates to orbital radius. Short answer question 7, 5 marks weightlessness and orbital forces, explaining weightlessness in the ISS as a state of continuous freefall where gravity is the only force, causing both the astronaut and the station to accelerate together, resulting in zero normal force. Should you require assistance, please feel free to connect via WeChat or WhatsApp and send an email. Thank you for your attention. Kindly note the details of Dr. Liu's VCE Physics, Chemistry, and Biology channels.